Hello, Glenn Porter here, and today's lecture is on understanding dynamic range. Now, in today's lecture, we'll talk about various topics associated with dynamic range. They include exposure values or EV values, subject brightness range, SBR, dynamic range, tonal range, graduating neutral density filters, high dynamic range imaging, and a new exposure concept called exposing to the right. Now, since you've come this far in the course, you would no doubt have experienced a lot of photographic language. Photography is full of jargon or has its own particular language in its own right. And that can be very confusing, but the concepts are fairly simple and fairly straightforward once you understand or once you get over that language barrier. I just want to explain or clarify some of that terminology that we use when we're talking about lighting, when we're talking about contrast ratios, when we're talking about dynamic range or lighting ratios in the studio and so forth. And there are three values to understand: ratio, factor, and stops. Now, you should all be fairly experienced with stops now. You know that one stop equals 2 times of exposure. So as we increase the exposure, as we're increasing the exposure by 1 stop, we're actually doubling or increasing the exposure by 2 times. When we increase our exposure by 2 stops, we're actually increasing the value of the exposure by 4 times, or quadrupling the exposure. So that should be fairly common sense to you by now, that 1 stop equals 2 times. Or if you reducing the exposure, it actually equals a half. So it equals half or doubling. So what this table does is sort of illustrate the correspondence of those values. For instance, a ratio is expressed as 2 to 1. It has a factor of times 2, and that equals 1 stop. When I explained the concept of a stop equaling doubling or equaling 2 times, I actually used the factor times 2. It depends on what you're actually describing in a photographic context to what value you might use. If you're using exposures, you might refer to it as stops. If you're using filters that have a light attenuating, or it prevents light from entering the camera, you might describe that as a factor. So the exposure factor or the filter factor is times 8, which equals 3 stops of light being blocked by the filter. Ratios are often described in other concepts of photography, like when it deals with lighting or it deals with subjects. For instance, a concept called an average scene is a scene in photography, a standard in photography, where it's a outdoor scene. It has equal combinations of highlight, shadow, midtones. It's basically an average scene, and it's lit by an average light source, which is the direct sun. Now, what's interesting about an average scene is that it has a subject brightness range of 128 to 1. So this is the type of example that we use ratios. It might also be expressed as 128 to 1 as a ratio, or 7 stop brightness range. So an average scene generally has a subject brightness range or ratio of 128 to 1. That's kind of how we use ratios. In the studio, when you get to the studio class, you will learn how to light the subjects at a particular lighting ratio, which is controlling the contrast of the light through the various lights, your shadow and main light sources. But you'll hear the expression the 2 to 1 lighting ratio, 3 to 1 lighting ratio, or a 4 to 1 lighting ratio. Again, lighting ratios actually use ratios. It's fairly obvious there. But you have to then convert what that ratio means into stops. So 4 to 1 lighting ratio is a 2 stops difference. So these three values are a way of expressing different numerical values associated with photography. So ratios, factors, and stops. We also have another value that I haven't exposed you to yet, and it's called exposure values, EVs. Now, you know, when you're talking about your camera exposure, you talk about three elements associated with the exposure: the f-stop that you used, the shutter speed that you used, and the film speed, or the ISO rating that you set on the camera, the sensitivity of the actual sensor. So a typical exposure combination would be f8 125th of a second at 100 ISO. Now that's a very long way to describe that exposure. EVs, exposure values, are a way of shortcutting that concept. So that EV value represents the exposure value of, for example, using the f16 rule, 125 ISO. We set our shutter speed at 125th of a second at f16. So 125th of a second, f16 at 125 ISO is equivalent to 15 EV. So that 15 EV is just a real shortcut way of expressing that exposure combination. Now, an equivalent exposure, as you know, through the law of reciprocity, might be f11 at 250th of a second at 125 ISO. That equivalent exposure is also EV15. It has the same exposure value. So exposure values is a way of simplifying that complex notion of shutter speed, f-stop, and ISO setting into one single number. Now, the interesting thing about EV values is that when you increase that one value, if you go from 15 to 16, you're actually increasing it by one stop or 2 times. If you're decreasing it from 15, as you can see on my little table there at the bottom, if you decrease it from 15 to 14, you're decreasing the exposure by 1 stop. An EV value from 15 to 13 is a decrease of 2 stops. An EV value from 15 to 17 is an increase of 2 stops. Now, it doesn't matter through law of reciprocity whether you've changed the f-stop and shutter speed, or you've upped the shutter speed because you want a faster shutter speed, but you've adjusted it with the right f-stop. So it gets very complicated when you're trying to compare exposures using the f-stop, shutter speed, and ISO setting. So EV exposure values are a way of shortcutting this concept of what that combination of exposure elements actually mean in a brightness value. Okay, so let's look at a concept called subject brightness range, often referred to in the literature or simplified in the literature as just SBR. A subject brightness range is a pretty easy concept, really. It's just the difference between the brightest highlight and the darkest shadow in your image, in the scene. SBR can be measured using a reflective spot meter if you have a handheld light meter. You can use spot meter readings in your camera, and if you measure the brightest area, but I will add something to that definition, brightest area with detail to the darkest area with detail, the subject brightness range is the difference of those two regions, either in stops or in a ratio. So subject brightness range, or SBR, is generally expressed in stops, and it's just the difference between the brightest area of the subject with detail and the darkest area of the subject with the detail. When we're evaluating the subject brightness range from image, it's really the light, contrast of the light, the contrast of the subject is inherent in the subject itself. So really all you need to do is measure the subject highlight with detail and shadow with detail, and that's your subject brightness range. So here we have a portrait, and I've just got some dots here. So if you wanted to measure the subject brightness range, you just need to measure the top of the subject's head, the darkest area with detail, and the subject's face, the brightest area of the highlight value. I wouldn't measure the whites of the eyes because there's no detail there. Well, you could argue there's detail, but I would measure certainly the highlight value of the skin. In this subject, we have a high key image as opposed to the previous low key image. So we have, in this instance, we have a high key image. So the difference of the subject brightness range is that highlight, which is the top the top little red dot versus the shadow underneath the egg. And this would be a different subject brightness range to the previous one. So subject brightness range is just that difference of contrast between the shadow and highlight with detail. Now, the whole essence of this lecture is about dynamic range and tonal range. So let's have a look at what dynamic range is. And let's illustrate that first of all by looking at an image. All right, now this is an image that I photographed on the Cairns campus. And just have a bit of a look at this image. It's not a spectacular image, but it's shot for the lecture. What type of subject brightness range are we dealing with here? We're dealing with a very high subject brightness range. We have the sky, which is very bright. Okay, it doesn't have detail, but it's quite bright. We have those fluorescent lights on those piers or those posts. And then we have the shadow area within the mountain range in the Cairns mountain range. Even the shadow area on the Cairns Institute building or the shadow area on the dental school building as well. This is a problem. This is a problem child when it comes to photographing, because our dynamic range of our cameras, which is the ability to record a range of tone highlights and shadows within a particular stop value. But the dynamic range of the camera cannot cope with this subject brightness range. So this subject brightness range, the sky, the lights, and the shadows far exceeds the capacity for the camera to record detail in all those areas. So as you can see, you're losing detail in those fluorescent lights, which are mounted onto the posts, and we're losing all that detail in the mountain range, which has wonderful texture there, wonderful detail in that foliage on the mountain range, but we're not able to record it. So we're losing detail in our shadow region in one end, and we're losing highlight detail in the other. And we're not able to record detail in both those areas because the dynamic range of the camera is not as broad or doesn't have the capacity to record that high level of subject brightness range. So what I want you to learn by looking at this image is to understand that there are limits to the recording capacity of the camera. When we're in this scene, when I photographed this scene, I could see detail in the lights, I could see detail in the shadow region, but my vision is very different to what the camera can record. So dynamic range is simply the range of values that from the brightest to the darkest area that can be recorded with that camera. Okay, so subject brightness range is the contrast of the subject, but dynamic range is the ability of the camera to record that range or a particular range, and there are limitations. So when you look at this image, you can see those limitations are evident. Lost detail in the highlights, lost detail in the shadow because the dynamic range the subject brightness range exceeds the dynamic range of the camera. Understanding your dynamic range is important to control the outcome of the image. So you've got to know the limits of the equipment that you use. It's not hard to understand that and be able to cope with it. But if you don't have control over it, you don't know, what happens to that image that we just saw. I could have placed my exposure to have detail in the shadow. I could have placed the exposure to have detail in the highlight, but because of the dynamic range, I couldn't control both under normal conditions. So let's look at dynamic range in a little bit more detail. So the dynamic range in digital cameras is an analog limitation of the sensor. So it's a physical analog limitation that the sensor can record. It's a limitation based on two elements: how much light it can record in the brightest areas and how much light it can record in the darkest areas. So let's look at the brightest area first. So the brightest scene information of the camera can capture is limited by the capacity of the sensor. At some point, the pixel wells can no longer accept more photons. So at a particular exposure, a particular part of the scene, the brightest areas of the scene, the pixel wells, you've got your little squares of pixels, and the way they work is that light hits those pixels, it converts the light energy into a current, and that current is then converted, that current is an analog signal, and that analog signal is then goes through an analog to digital conversion, an AD conversion, and that conversion then, that analog signal or current is converted into a digital signal, which is made up of zeros and ones, that binary code, as you know. So the capture device originally, though, is analog. So the way the sensor works is an analog response to light. It converts light energy into a current. The more light energy, the more current. Except there is a limit to there's a limit to the actual current that can be produced. Once a pixel well, which is a square pixel, has come to what we call saturation point, even if you produce more light, it won't produce more analog current. So pixels themselves have a saturation point. And once that saturation point is exhausted, it cannot produce more current, therefore can't change variation of the digital signal. So the brightest part of the element, the brightest part of the scene, I should say, at some point the pixels will no longer accept any more photons, any more light energy. That means that it's reached saturation, therefore it can't record anymore. So there's a limitation to that analog device. Once it's reached saturation, that's it. It can't change. Now, the interesting thing about the other end of the dynamic range, the shadow range or the darkest area, is that it's not the same situation. It doesn't reach a minimum saturation, or highlights reach a saturation, but the minimum doesn't actually reach a sort of saturation point or a threshold. What happens in the shadow areas is that with less and less photons on the pixels, you get more and more noise. So the limit to the dynamic range in the shadow region is a subjective one, in the sense that it depends on how much noise you're willing to accept. So while the highlight saturation point can be empirically kind of measured, the darkest shade is somewhat subjective. Some people would accept more noise, some people won't, so it just depends, but that is a bit problematic. But the weaker signals in the shadow region produces a small amount of photons, which then produces noise. Now, we'll talk about that a little bit more later on in this lecture, when we talk about how these digital devices actually work in a linear fashion as well. I think this definition kind of captures what dynamic range is, both for silver halide, which is film, and electronic imaging sensors. So the dynamic range of both silver halide and electronic imaging sensors refers to the ratio of the highest to lowest level of radiation in visible imaging light sensed by the sensor. It generally relates to an imager's ability to record both bright and dark objects in a scene with the same exposure setting. So one single exposure gives you the ability to record detail in the highlights, detail in the shadows. That's kind of what we're trying to aim at. But that will depend on the subject brightness range. You get scenes that have greater subject brightness range, more contrast, like the scene I showed you in that earlier photograph, and the physical capacity of the analog signal in the sensor. Now, in the previous lecture, we talked about bit depth or pixel depth, and it's important that you understand what pixel depth is before you look at this lecture. So if you haven't looked at pixel depth, stop now, go and listen to the pixel depth lecture and then come back to this point. What's interesting about pixel depth is that it's often confused with dynamic range, and it's deliberately confused with dynamic range by camera manufacturers that exploit this confusion and make statements to say that their cameras have a 14 stop dynamic range. So marketing do use these tricks. They confuse pixel depth with dynamic range. So what I'm going to try to do is attempt to separate that, because dynamic range is the capacity, as we just discussed, the capacity to record a range of the brightest and darkest tones that the camera can record. And bit depth actually refers to the tonal range, how many variations between those 2 points. So dynamic range is a different concept to bit depth. Now, if you remember from our pixel depth lecture, we have the bit depth determine how many different variations of tone was able to be produced by that bit depth. So in an 8-bit depth image, we had 256 different tones, and that was considered the threshold of quality, photographic quality. 256 was equivalent to the appearance of continuous tone prints. In an RGB file, an 8-bit RGB file, that's usually 8-bit per channel. So 8 bits for the blue, 8 bits for the red, 8 bits for the green, or I should say 8 bits for the red, green, and then blue. And the reason why we shoot RAW photographs, or the reason why we shoot in the RAW format, is because it offers a greater bit depth. So we can shoot in the 12 or 14-bit depth rather than the 8. JPEGs are processed to 8 bits per channel, and our RAW, we process it at 16-bit, which gives us 65,500 different variations. So that table's a handy one to refer to in the next concepts that we're going to discuss. Okay, so this is the conceptual framework that I really need you to understand, the difference between dynamic range and tonal range. The way to explain this is by the ladder analogy, and that's why you may have noticed a lot of ladders in this lecture. So here we have our single step ladder. We have on the left hand side our minimum recorded density, and that minimum is determined by the level of noise. It's a subjective level. On the right hand side, on the last run of the ladder, we have our maximum recording intensity, which is a physical saturation of the photons in the sensor, in the analog sensor. The difference between the minimum recorded intensity and the maximum recorded intensity is generally described in stops. So you might hear a camera having a 6 or an 8 stop dynamic range. That's how it's expressed. That means that there are 6 or 8 stops between that minimum and maximum dynamic range. Now, when we talked about pixel depth, we talked about the variations of tones. So the way you can think about the difference between dynamic range and pixel depth is that pixel depth determines how many steps that are recorded in between that minimum and maximum. For example, the image I've got on the screen at the moment, a 2-bit pixel depth, if you remember, has 4 different tones. A 4-bit tonal range has just those 4 steps within the ladder analogy. We still have the same minimum, we still have the same maximum, we still have our noise and saturation limitations, but we only have 4 variations in between those 2 points. Unlike an 8-bit pixel depth image, we now have 256 different tones, or 256 different steps within the ladder. Each step is a tonal value. Now, I can't physically fit 256 steps on that ladder in this diagram, but you have to visualize that, and I'm sure as visual people you could do that quite easily. So within an 8-bit pixel depth image, we have now a tonal range that went from 4 steps in the ladder to 256 steps in the ladder, or variations of grey and black. So dynamic range is that minimum and maximum recording capacity, and tonal range is the amount of variation of shades between those 2 points. The dynamic range is an inherent quality of the sensor or camera that you're using, and the tonal range can be controlled by the bit depth that you apply. So let's just take a breath and then let's just reanalyze these 3 concepts that we've just discussed. So subject brightness range, dynamic range, and tonal range. There's 3 elements that we've just explored in this short lecture. So subject brightness range is the contrast of the subject expressed as stops, usually in stops, sometimes as a ratio. It can be expressed either way. Dynamic range is always expressed, mostly expressed in a stop value. It's the ability to record shadow and highlight detail, the maximum and minimum range that the camera is capable of reproducing. And tonal range is the amount of tonal variation in pixel values, and that's controlled by the pixel depth. So when you're shooting a raw format photography, and it depends on what camera you've got. Some cameras will be a 12-bit raw file, others would be 14-bit. We generally say we call it 16-bit, but they're not really 16-bit. It's either 12 or 14-bit in most cameras. Depends on the camera manufacturer. But the amount of pixel value differences that you get in a 12-bit is around about 4,000 different steps of grey between the brightest and the minimum. Now, why is this important? This is important because quality is often not about sharpness. Quality in a print, in a photographic print, is about tonal range. Quality is generally defined by the end product, which in most cases is a print on the wall, a print in a folio. It may be the end point in advertising photography. Fashion photography might be the image in a magazine in graphic reproduction. The end point for an image that goes on a web page is the dynamic range of the actual computer and the actual screen-based concept. But what I want to do is sort of concentrate on the highest quality. And the highest quality isn't graphic reproduction in magazines. It isn't screen-based imaging. It's actually a print for exhibition quality. To maximize or to achieve high quality in a exhibition quality print, it should have an extensive tonal range, because that's the number one law of quality, tonal range. The goal generally is to match the subject brightness range, the dynamic range of the camera, and the print density or tonal range of the print itself. That's kind of the end goal. If you match those 3 elements, you're going to get a good quality print. George de Wolf's concept of quality. It is manifestly important to understand that controlling the dynamic range, the textual range, and the luminosity or brightness component of an image in either color or black and white is the basic key to all successful images. Now, this is going to be a very strange concept for you right now, being exposed to those 3 elements: subject brightness range, dynamic range, and tonal range. It's going to be very confusing for you right at this moment if you're listening to this for the first time. You will need to probably listen to this lecture a few times to get the full understanding of what those different values are. But what I want you to do is learn what this means and then start to think about it as your photography is developing. Because at some point in your career as a photographer, you'll get this quote by George de Wolf. You'll get it because you'll be applying it. What I want you to do at this moment is understand the differences of those concepts and start thinking about it as your photography develops over the next few years. Photography is a long end game. It takes years of practice to actually get very good at it. You start to get good in different areas at different times of your career. You might have a great creative eye, and your composition is wonderful at this stage. You might need to develop your creativity. You might have good technical skills of exposure. You might need to develop technical skills of exposure and light reading. But by the end of this journey for you, to achieve quality, to achieve those beautifully crafted exhibition quality prints, you will need to understand this quote, and you will understand this quote at some stage down the track. It won't be tomorrow, it won't be next week, it won't be next year. It'll be at some stage down the track. I don't know when, but what I want you to do is start thinking like this now and start to learn how to appreciate what quality means. Okay, what I've tried to do here is try to put all that sort of information together in a pathway for you, a tonal range pathway. So our subject is controlled by the subject brightness range. The camera has limitations in the dynamic range. Our processing, whether it's in the capture or the image processing, the raw file, is captured in the bit depth, which is our tonal range in our digital image. And then the print quality is determined by the tonal range or density range of the actual print. So subject, capture, process, print, that's the pathway that we're kind of looking at this ultimate quality of exhibition quality prints. It's all those things. It's not just the process, it's not just Photoshop, it's not just the capture, it's not just the subject, and it's not just the print. It's all these elements combined. And that'll take you a while to get a good control over all those four elements. One of the reasons why it'll take you a while to get good control over it is because photography isn't easy. Photography is a difficult thing to do well. And it's difficult to do well often because of these problems. We always have things that challenge us in photography, and this is one of them. The subject brightness range is greater than the capacity of the dynamic range of the camera. This image that we see here of a photograph taken in, it's an interior photograph but taken through the window. So we have a very bright outdoors, a very low level of illumination indoors. The camera doesn't have the ability to record both the bright values outside and the low values inside. So you have to make a decision. Where am I going to lose detail? In this case, the detail's lost on the interior, and the details of the exposure is recorded of the outdoor luminance brightness, so luminance value. So you have to place your exposure somewhere that's aesthetically pleasing and doing what you want. But unfortunately, we can't get both the inside and the outside to record because of the lack of dynamic range. The subject brightness range is exceeding the dynamic range of the camera. Now, there are things that we can do. We can control it. One way of dealing with this problem is doing what the photographer's done here. This is quite a nice photograph. Has made a decision. Well, I don't want detail inside. I want that to be black, and frame the image. So we have a frame within the frame. So that's one conscious decision that you can make. However, when you're trying to get photographs of subjects that you do want detail, what do you do? If you're shooting fashion, they're not going to want this type of image. They're going to want all the detail in the image. So what do you do when you get these type of subject brightness range? Let's have a look at some possible options. So what I've got in this chart is a range of either display, which is output, or capture type of subjects, and we look at the approximate dynamic range of some of those subjects. So outdoor sunlight gives us a subject brightness range of around 100,000 to 1, which is 17 EV. We're talking about very dark subjects and very bright subjects. An average scene, which you get a mixture of both, is actually 15 EV, but that's outdoor sunlight, which is us. It's a very contrasty example, that one. Human eye has the ability to record a dynamic range of around 20 EV, 20 stops, which is around about a a billion to 1 ratio. So this is one of the other challenges that we have with photography. What we see and what our camera can record are two different things. Now, I talked about this in perspective about the two-dimensionality of photographs, and we see in 3D, but the camera's capturing in 2D, and we need to be able to train ourselves to see like a camera, because our camera can never see like our eye. Same thing, same deal with dynamic range and tonal range and all those things. Our eye can see much more detail than the camera, and you have to kind of train yourself again to see like a camera, to appreciate what the camera can record, not what you can see. One way you can do that is slightly squinting your eyes, and that gives you a similar dynamic range as what your camera can record. Negative film has a dynamic range between 1000 to 2000 to 1. Computer monitors around 500 to 1, which is 9 EV, 9 stops. A digital SLR camera, typical digital RSL camera, 300 to 1, which is a 6 to 8 stop range. High glossy prints, this is now we're talking about output, has a 200 to 1 or 7.6 stop range. Compact digital cameras, 100 to 1, it's about a 6 stop range. Glossy prints 100 to 1, slide film 64 to 1, 6 EV, handmade matte prints 50 to 1, graphic reproduction, which is brochures, catalogs, magazines, 16 to 1, which is only a 4 stop EV. So we can see that our outputs and inputs are quite varied, and how do we match all those? That's quite difficult. Now, one way of looking at this is by looking at zone system, and Ansel Adams was one of the fathers of the zone system. He's claimed to be the founder or the inventor of the zone system, but I dispute that. I think he took other people's ideas and systemized it, but those ideas were by Paul Strand and Fred Picker, other photographers for many years before Ansel Adams. But I think he could be credited, I think, for systemizing the zone system. And the zone system in black and white photography is looking at breaking up those tonal values as zones, as one stop or stop values. Zone 5 is a mid-grey or a grey card, 18% grey. Our highlight values go up and our low values go down. Now, I guess one of the ways you can look at this, but you need to do a bit more reading about this concept, and I'm not going to explain about it a lot here, but it's looking at the difference between a full range, a dynamic range, and a textured range, and then a graphic reproduction range. So in a full range in the zone system, we've got 10 stops, or it's actually 11 different shades, but 10 stops difference between 0 and X, 10. A dynamic range is 1 stop either side, so zone 1 to zone 9. Now, zone 1 is generally black without detail, and zone 9 is white with no detail, but slightly, still has no detail, but slightly less than paper base, black, D max and D min. The textured range is where we kind of record most of our portraiture. Most of our subject range, we like to have detail in the shadows and detail in the highlights. So that's that textured range, which is 6 stops. Zone 2 is this first hint of detail, and zone 8 is the first hint of detail in the highlight. Zone 2 is the first hint of detail in the shadow. Zone 3 and zone 7 is more the graphic reproduction range. So if you're shooting fashion work for magazine reproduction, you need to make sure it's within that sort of range. So just a way of conceptualizing what different type of tonal ranges can mean. So dynamic range, 8 stops difference. Textured range, we're getting a lot of detail in shadow and highlight. That's a 6-stop range. And a full range is sort of 10 stops. All right, so let's look at how we can control excessive subject brightness ranges. There are a few different ways. If we're shooting in the studio, it's easy. We can decrease the lighting ratio. We can what we call fill the shadow region by using lights. So we light up the shadow region to make it less contrasting. If we're shooting outdoors or on location, we can use a technique called fill flash. So we use portable flash to act as a extra light to fill in those shadows and reduce the subject brightness range. Because remember, subject brightness range is a combination of the contrast of the subject, the tonal contrast of the subject, and the contrast of the light. So by introducing more light, you're reducing that shadows. You can select under natural light sources. You can go for lower contrast, so take the subject out of direct sunlight, which is high contrast, and move them into the shade where you're using clear blue sky, so your lighting ratio or your lighting contrast is reduced. You can also wait till the light changes, so you can wait till the light goes behind the sun goes behind a cloud, or the cloud moves over to the light, or you can wait to dusk or dawn, get up early in sunrise, or wait at dusk, and that will actually reduce the contrast as well. You can use a technique, an optical technique, by using graduated neutral density filters. I'll show you a photograph of them at the moment. But one of the problems that you get in landscape photographs is that the foreground subjects, if you're shooting with sky in the background, the sky is a lot brighter than your foreground subjects. So you've got the option to expose for the foreground and blow out the detail of the sky, or expose for the sky but then make the foreground content too dark. So you've got that, always got that sort of element to deal with. One of the ways you can deal with that is by using graduated neutral density filters, so that you can actually attenuate the light in the sky. A method called exposure blending methods, where we take an exposure for the highlights, exposure for the shadows, exposure for the midtones, and then we use layers in Photoshop and blend them. That's a exposure blending. So when we shoot for the highlights, we're recording the detail in the highlights. When we shoot for the shadows, we're recording detail in the shadows. And with the midtones, we're just getting a nice clean midtone. And we can then combine those three, or even just two exposures, by using layers in Photoshop. And the last option to control excessive subject brightness range is using a software tool called high dynamic range imaging, which is similar to exposure blending, but the actual software does it automatically. So in exposure blending, we kind of do it manually in our film processing, our image processing. But with high dynamic range imaging, you can actually do it automatically. Photoshop has high dynamic range capacity, and there's high dynamic range generic software that you can get to use it. You might even notice in your iPhones or your mobile phones has HDR, high dynamic range imaging option, and when you use it, it'll take 3 photos and then process those 3 photos into the one image. So graduating neutral density filters, I've already explained what this is. It optically attenuates the skies or the bright areas within the frame. You usually have different values, density values, 0.3, which is 1 stop, 0.6, which is 2 stops, and 0.9, which is 3 stops. Remember, density is the log of opacity. And you can also get soft and hard transitions between the neutral density areas. And the idea of this, if you particularly think of landscape photographs where you're trying to reduce the brightness of the sky and to bring the subject brightness range down to the dynamic range of your camera, so you get the clouds, you get detail in the sky, you don't just get this blank sky, and that improves the aesthetics of that landscape photograph. So these are 3 different graduating filters that you can see there. As I say, you can get them in different densities depending upon the subject brightness range you're shooting, and you can get them in a hard or a soft transition between nothing and the density. So just quickly, I just want to sort of show you some results. I've not shot high dynamic range, I've borrowed these from the internet, but just to illustrate this type of concept as well. So high dynamic range imaging, you can see the image on the left is your typical standard image, photograph of a model inside a building, inside an old derelict type building. We can't see any detail in the ceiling, that's lost in the shadow region. The highlight within outside of the windows is blown out. We've lost all that highlight detail. So we've got no detail in the ceiling, in the shadow region, no detail in the highlights. By using the HDR imaging software, we now have detail in our shadow region in the ceiling and detail in the highlight area, which is outside. I mean, that's probably easy a 10 to 12 stop different range that's seen between the darkest, the subject brightness range, the shadow area in the ceiling, and out the brightest area outside. It's probably 10, 11, 12 stops. So far exceeds the dynamic range of normal digital SLR cameras. So this is just basically how this HDR software works. Allows for greater subject brightness range recording in the dynamic range of the capture device when the subject brightness range far exceeds the dynamic range of the camera. A series of exposures is recorded, and same with blended exposures. You obviously got to shoot this on a tripod, so you get 3 images that are registered. With HDR, you can shoot 3 images, you can shoot 5 images, you can shoot 7 images. There's a little calculation you've got to work out depending upon the total subject brightness range. So the greater the subject brightness range, the more images you have to shoot to actually blend. The HDR software processes the tone in a 32-bit map. This is quite powerful processing. So it reconfigures the image so that when we're viewing it on screen or viewing it out on a print, it actually fits the dynamic range of the output. This is a good example of HDR imaging inside a train tunnel. Don't suggest anyone does this, quite dangerous. This is not using flash, it's not using any light, it's using HDR. So you can imagine how dark that tunnel was compared to the outside of the bridge illuminated outside of the tunnel. Huge dynamic subject brightness range. Yet with HDR imaging, and this would actually be 7 and maybe even 9 images, but in this high dynamic range imaging result, we're getting detail all through the shadow region, all through the highlight region. The problem with it, if you haven't noticed already, is that HDR gives you a very surreal, very unnatural feel. And that's some of the criticisms with HDR. You can use it aesthetically, but it does give you kind of a surreal type look because it's not natural. But it does expand the capacity of the dynamic range. That's why it's called high dynamic range imaging. But it expands that capacity of your camera's dynamic range by using this type of software and process. So this is another image I borrowed from the internet, and you can see sort of in the exposures that occurred in the 3 exposures, 2 EV, 0 EV, and -2 EV. Now, what does that mean? You should remember EV. So 0 EV is the indicated exposure, the normal exposure if you like. 2 EV is +2 stops, and -2 EV is -2 stops. Remember, 1 EV actually equals 1 stop. It's not a factor. So when the HDR maps, you get that sort of final result where you can see detail in the curtains. There's actually detail in the curtains. You can see detail in the ceiling, that painted motif in the ceiling. You get that beautiful tonality and texture and detail of the parquetry floor as well. So here's another outdoor shot. This time there's 4 exposures, not 3. And you have a very bright sky compared to a very dark sort of shadow on the side of the little hut. And in the HDR processed image, you can see that there's detail in that shadow region and detail in the sky. If you look at the +2 EV image, you see that sky is quite blown out, but you get nice detail in the shadow region, whereas the -4 EV, and it's gone -4 EV to pick up that detail in the sky. You get that beautiful sky detail and cloud formations, but the shadow region's completely clogged up. So the mapping kind of takes that shadow region of the 2 EV and remaps it, and takes that detail in the sky and remaps it into a single image. This is a much more natural looking HDR shot than the other ones, but it still has that sort of edge of unreal to it. But like I say, that edge, that surreal type feel can be used aesthetically for your photography if you like this type of work. And one of the assignments is HDR for your report. So you can see the results of this image using HDR. Some HDR software, you actually have kind of a scale. You've got a reality, a more real tonal mapping process, or you've got a surreal tonal mapping. You can actually control that a little bit in some software applications. This is obviously going more towards the surreal, and so is this image. But that strong aesthetic is quite nice, quite contemporary. Okay, just one more thing I want to sort of discuss before we finish up, and that is the concept of tonal mapping via digital cameras. Now, there's a few differences between traditional film recording and digital sensors. The first is that they're actually both analog. They're actually both analog signals to start off with, but then the digital one gets processed. But the film recording is a non-linear response to light. Now, if you see that curve on the left-hand side, that is a characteristic curve which represents the response of density on the film caused by exposure. And from the bottom left-hand side, that's our shadow region, and you get this sort of S-shaped sort of curve. So there's some compression of tonality in the shadow region, and there's some compression in the highlight region, which is on the top, or what we call the shoulder of the curve. The shadow region on the bottom of that curve is called the toe of the curve. But it's non-linear, and that gives us a nice sort of quality, which is an interesting aspect. Now, the chart on the curve on the right-hand side is the digital response, the digital sensor. Digital sensors are linear, have a linear response to exposure and light, unlike film. Now, that can cause some problems, and let's have a look at it. Okay, so here we have a ideal continuous tone grayscale. This is created digitally. I created this digitally on the computer. But what it sort of represents really is our dynamic range and our tonal range. Our dynamic range, remember, is the minimum and maximum that the camera is able to record. So our minimum is our black and our maximum is our white. And our ideal tonal range is expansive. It means that there's as many different variations between those 2 points. That gives you your quality. Tonal ranges gives you your quality. That's controlled by bit depth. What we've got is a ideal continuous tone. So it goes from the black and it graduates into the grey and then graduates into the white in an even way. That's what we would expect our digital sensor to record and respond to light. But because it's lineal, it doesn't respond that way, and that's a problem. Now, I hope you can see this on your monitor that you're looking at, because there's some subtle differences here, but they're important differences. The digital continuous tone grayscale looks more like this on the bottom. Now, what can you notice with this grayscale compared to the top? We've got our minimum, which is on the left-hand side. We've got our maximum, which is on our right side. Our gradual continuation between black to white is disrupted. You might notice that on the right-hand side, the highlight is shifted all the way over to about halfway. So our shadow region, our blacks are compressed, our mid-greys are compressed, or our sort of in-between mid-grey and grey are compressed. Even our mid-tone is compressed. But then we have a long tail of highlight. So this is the difference between film grace tonal values or tonal range and digital tonal range. It's because digital capture responds linearly, in a linear way, to exposure. The bottom tonal range is the result we get. Now let's kind of put some practical sense into this. So what are we dealing with? All right, this is our typical camera. We have a 6-stop dynamic range, so 6 EVs or 6 stops difference between the highlight and the shadow, or the darkest and the brightest areas that the camera can record. We're shooting in RAW format, which in the Canon cameras at the current time are 12-bit RAW capture. 12-bit RAW capture gives us 4,096 different pixel variations. That's our tonal range. But let's look at the stop values in our dynamic range. We have our shadow and our highlight either side, and we have grey values in between. So what I'm trying to get across here is that distribution of pixels. We now have 4,096 different pixels, different tonal values, pixels. Because of the linear nature of digital sensors, these 4,096 variations of grey are not spread across the dynamic range evenly. Instead, as you can see on the bottom diagram, the first stop, the highlight value, because it's linear, it actually takes up half of the pixels. So in our first stop in our highlight range, we have, in that highlight value, we have 2,048 pixels in that one stop value. We then go to the next stop, which is a half again. So we get 1,024 pixels, different shades within that dynamic, within that stop range. Then we go one stop less again, and we get 512 pixels. We go one stop less again, and we got 256, then 128, then 64. So what we've got here is a much greater ability to record detail in our highlight values because we have more pixel depth in that first stop. We have very limited pixel depth in our shadow region, which only in this scenario only has 64 different variations. What this results in is that with very limited ability to record tonal values in that sixth stop, that darkest value, we start to get noise and a corruption or artifacts in that region. So that's one of the problems with digital capture, is that in our shadow regions we start to get this noise effect because it has less pixels to actually expose and create value. What I'm trying to show in this is that our tonal range in digital capture isn't that ideal continuous tone. Because of the linear effect of digital sensors, we get a redistribution of the pixel values across that whole dynamic range. More in the highlights, less in the shadows. Now this is the concept of a new exposure method. This is the basis of a new exposure method called exposing to the right. Now it's a fairly controversial method, I have to say, but it's an interesting one. I use it and I don't see a big difference, but there is some difference, particularly if you're shooting landscape work with a high area of shadow detail. So let me just read out the quote. A fairly recent concept, the idea of exposing to the right is a technique used with RAW capture, not JPEG RAW capture, to better distribute the levels available after quantization while aiming to avoid clipped highlights and reduce noise and contouring in the shadow areas of the image. So I'll explain what that means. Have you ever seen in some of your images that you get this jaded or contouring effect in the shadows? That's because there's not enough pixel depth to actually record variation in that shadow region. So you get contouring, you get noise, you get all those artifacts. What this technique does is you use the histogram, you do a test shot, you look at the histogram, and if you're shooting within, say, a 5-stop or a 6-stop range, within your dynamic range of your camera, you move the exposure to the right, to the histogram, you move the histogram to the right, which is shifting over those highlight values, which then better distributes that first stop and gives you more pixels to work with in the shadow region. Now the key thing is you don't just overexpose. It's called exposing to the right. So you shift that first level of highlight in your histogram over to the right hand side of the histogram, but you don't clip. When you move it over too much and you start clipping the highlights, you'll lose detail in the highlights. Exposing to the right is shifting the histogram over to the right, so you're moving that highlight value over to the edge of the histogram to allow for better reproduction in your shadow regions. That's all it is. Now what's interesting is that Canon, I've never used this, so I don't know how it really works. Don't know if it works, but there's a thing called a highlight tone priority, which in my thinking is an automatic system of shifting your exposure to the right. So you can do it automatically on the cameras now. It actually thinks for you. So highlight tone priority. Check it out. It might work for you. So shifting exposure to the right is a way of trying to improve the detail and minimize artifacts in your shadow region. What it does look like though on your screen, when you're looking at the screen and when you start to process these through Adobe Camera Raw, the images look too bright, and they are too bright. But when you're processing the image, you then readjust the exposure. So you bring that exposure value back down so it looks correct, but you've then got those pixel depth already embedded into your shadow region. So it's not just leaving it at that exposure, it's being able to record that detail in your digital image, in your digital raw file. Once you've got it in there, once you've got detail in your shadow region, you can then play around with it. And even if you reduce the exposure, it's going to reduce the detail in the shadow region, but not create noise. It'll just make it go darker because it's got more detail in there to start off with. So have a bit of a play. See whether this technique works for you. If it doesn't, it's fine. But it's just another option to get good quality images. One of my favorite quotes by Moholy Nagy: the illiterate of the future will be the person ignorant of the use of the camera as well as the pen. Beautiful. Okay, I hope I didn't hurt your brain too much in this lecture. It is rather technical. You may need to refresh and go over this a couple of times. It's important in your development as a good practical photographer. These concepts will take weeks, months, maybe years to start to master, and you become in control of these elements. But they are something you need to be conscious of. You need to understand how they work. You won't be able to apply them straight away, but don't worry. But reflect on this as you're starting to build up your skills and technical abilities in photography. Because understanding dynamic range, understanding subject brightness range, understanding tonal range is the key for quality sometime down the track. Well, thanks for listening, and I'll talk to you soon. Bye-bye.